Hi, welcome to Lambda U. My name is Andy and I'm a Solutions and Support Scientist at LICOR. In the previous courses in this learning path, we discussed a variety of topics related to your Western blot protocol, including sample preparation, gel preparation, and transfer. If you need a refresher on any of those steps, please refer to those earlier courses. After transferring the proteins from the gel to the membrane, the next step is to block the membrane. In this course, we'll discuss why we block the membrane, different methods and solutions for achieving this, how to optimize this step, and some tips and best practices to help you get the best results. At the end of this course, you'll know all there is to know about membrane blocking, and you'll be well primed to nail the blocking step of your Westerns every single time. Specifically in this course, we'll be looking at blocking the membrane in preparation for near-infrared or NIR detection. Near-infrared detection is a fluorescence detection method which is commonly used in quantitative Western blot applications. In contrast to the more traditional approach of using chemiluminescence, NIR detection gives us stable signals which are highly proportional to the abundance of the detected antibody, which allows for accurate and reliable quantification of targets within the linear range of the assay. Additionally, NIR detection allows us to multiplex, which means that we can detect more than one target even if the bands co-migrate and overlap. Let's start by having a look at how near-infrared detection works. In near-infrared Western blot detection, proteins extracted from a biological sample are separated on a gel according to their molecular weights, and then transferred to a membrane. After the empty space on that membrane has been blocked, a primary antibody specific to the protein of interest is then added, and this in turn binds to that protein on the membrane. Following this, there are two ways that we can visualize and quantify those targets. The first is to use a labeled primary antibody, which is then directly detected. This is unsurprisingly called direct detection. This is a great method in principle, but in practice, labeled primary antibodies are considerably more expensive and harder to obtain than their unlabeled counterparts. The alternative is to use indirect detection using a labeled secondary antibody, which is sometimes called the detection antibody, and this is then used to detect an unlabeled primary antibody. This is a much more common approach, as only a handful of labeled secondary antibodies can be used to detect thousands of different primary antibodies. Also, multiple secondary antibody molecules can bind to a single primary antibody molecule. This causes an amplification in the signal and gives us better detection sensitivity. For fluorescent detection to take place, the secondary antibody has to be labelled or conjugated to a fluorophore, also known as a dye. We then use a light source, such as a laser, to excite that dye. When the dye is excited, it gives off light at a slightly different wavelength to that which was used for excitation. This emitted light signal can then be measured using an appropriate detector, such as an avalanche photodiode or a camera chip. Near-infrared detection uses fluorophores that emit in the near-infrared part of the electromagnetic spectrum, where background is greatly reduced in comparison to visible wavelengths. It's important to realise that detection sensitivity is determined by the signal-to-noise ratio, or SNR for short, which is the ratio of the emitted light signals to that of the background light level or noise. Therefore, using near-infrared wavelengths where the background level is reduced gives us greater effective sensitivity than visible wavelengths where the background is much higher. If our Western blot imager has multiple channels, each one tuned to a wavelength distinct to a particular dye, then we can distinguish different dyes in our samples. This means that we can multiplex our detection. For example, if our imager has two independent channels, then we can detect and quantify two targets, even if they have the same or similar molecular weight. For more information on this process, please refer to the secondary antibody incubation course here on Lambda U. Now we've reviewed how near-infrared fluorescence allows us to detect proteins on the membrane, we're now ready to move on to the blocking step of the Western blot protocol. In the next lesson, we'll discuss why we need to block the membrane and ways that you can prepare for this step.